continue with the previous lecture. So when we roll 4 dice, we get at least 1 6. The second option is we can just use the complement event. So if you have at least 1 6, that means it's the opposite from no 6. So that's why here is 1 minus no 6. So the no 6 is what? That means the first one can be other than 6. No 6 actually is 5 over 6. The chance, one dice is not 6, is 5 over 6, right? Because you have either 1 or 2 or 3 or 4 or 5. They are all no 6. But this no 6, remember, is 4 dice need to be no 6. So that's why at least 1 6 is the complement of no 6 for all 4 dice. So that will be 5 over 6 power to 4. But don't forget, we need to do the 1 minus. So that's our at least 1 6. So you can do either option, okay? But one thing we just want to show you, yeah, the option 2, at least 1 6 actually is the complement of no 6. So we're just using the 1 minus no 6 is 1 minus 5 6 and power to 4. Then we see the result in the Python. So that's the chance of no 6 in 4 dice, in 4 rows of a die, right? So that's why the probability for the no 6 in 4 rows, that will be 1 minus, okay, so 5 over 6, okay, so we say power to 4. So that's we will get the result, okay. So that's mean. So if you want to get at least 1 die, yeah, 1 6 in the 4 row of the die, so that's 1 minus here earlier our probability of no 6. Okay, so 1 minus. Okay, so that's the result. So that's just one. You roll dice 4 times without 6. Okay, repeat. You roll dice 4 times, at least 1 6. It's like this. So how about we want to roll more times? So the chance to get at least 1 6 in n row of a die. And we want to see, can we just see all of that? Okay, so that's why we create a array. So then we will have from 1 to 50 rolling dice how many times. So then we want to get at least 1 6 from that rolling. Okay, so you can roll 1 time, 2 times, 3 times, but all the result is at least 1 6. What is the possibility? So that's why here we create an array. Okay, so that's from 1 to 50. So we create a table. The first one is rows. Okay, so your rows is the array. Okay, so you roll 1 time, 2 times, 3 times. Then the second column is a chance of at least 1 6. So that's why they will be 1 minus 5 over 6, depends on how many times you want to roll. Okay, so then we see the table look like. So we only show you the first 10 rows, but you can see at least 1 6. According to the rows times more, you roll more times, the chance just getting higher and higher. So let's see the visualization. So let's make this table in the scatter plot. So that's what you can see here. You see almost like I see earlier is our say 10 times. The 10 times, you rolling dice 10 times, at least 1 6. The percentage more than 80%. 20%, 20 times, at least 1 6. You see almost one. I think maybe 30. Yeah, 30 even. It's very close to 100%. So that's why here we just want to show you. You know, yeah, of course, you're rolling a dice more times, like 30 times, you never see at least 1 6 showing. Possibly some people want to trick you. Okay, we can show them the scatter plot on this table. So the quick summary about the problem solving method. We introduced you multiplication rule, addition rule, and complement. So ask yourself, when the first trial for your question, if that clear to answer, so then probability you know, almost certainly you can continue the process with the multiplication rule. Then you just see the beginning, the outcome, then they maybe have the combination of queen and the queen and the king. So that's why you have the first one need to be queen, the second one need to be king. So that's why we multiply. If no clear answer, right, we need to go back to the definition for the probability. Is all the outcome adding together divide by all the outcome for your specific event adding together divide by all the outcome for the whole possibility. Okay, so then we just add together. You list all the combination, divide by all the combination for the certain outcome you're looking for, divide by all the outcome. And sometimes the problem is too complicated. Like earlier we said at least 1/6. Then when you want to list all your output, okay, so actually it's a lot. So instead of list all the output, how about we think the other way? When we say no 6, at least 1/6, that's equal to 1 minus no 6. So that's another way to think about the problem. Maybe they are complementary problem. Okay, so that's the probability we want to talk about. So the next one, before we finish, we want to show you the very famous problem. So this problem is the game show host used a lot. And sometimes you see that on movie, especially the movie 21 has this question they discuss. Like, the show they say, the movie say in the Harvard school. Okay, so that's we call the Monty Hall problem. What is the Monty Hall problem? That's a game show. Okay, so the winner need to see at the end, can they get the car or not? So behind the 3 doors, one is car. Okay, so the other 2, of course, not car. So they say that's a goat behind that. Okay, so that's why that's mean. No matter what, from the beginning, the car will be 1/3 chance behind that, right? Okay, but they always like to make the show kind of even more attractive. So the game show host will give you a chance. So after you pick one door, okay, remember 1 is car, 1/3 is car, so 2/3 will be the goat. After you choose one, either one, okay, but the game show host always can find 1 is goat, right? Remember, no matter you choose the beginning is car, then they have 2 goats can open up. If you choose 1 goat, the other one will be car or goat. So the game show host always can open 1 door for you. Then they show you that's a goat. So they always ask you, okay, should you switch or stay after 1 door is open? If you see that in the movie, right? The movie told you, you always switch. But why? Okay, but why? So then that show you, if you forget how the probability is, but then we will show you, you should always switch. Why we told you, then we show you from the probability point of view. Because this one become a conditional probability. Okay, so we see here, we just show you this one, then we show you on Python. Your choice, right? You have 3 choices. Goat 1 and goat 2 and the car. We just say like this. If your choice is the first goat, we just make the goat. You have 2 goats, we make the first goat and second goat. If your choice is the first goat, the game show host, they will reveal the second goat, right? So that's why if you switch, you will get the car. Then if you choose the second, if your choice is the second goat, that door, the game show host always show you the first goat. Again, if you switch, the second one, have you switch? Actually, the other choice is the card. Then if your choice, original choice is car, right? Okay, so then they will show you either one for the goat. Of course, then the other choice is the goat. That's because we change your condition. Okay, originally, of course, it's 1/3, but after the game show host give you a condition, yes, you can either choose stay or switch. You always should switch because originally your choice to get a car is 1/3. Then if you switch, right, then become your chance to get the car become 2/3. That's what we call, that's very famous problem, Monty Hole problem. Because think about this way. Your original choice to get the car is 1/3. Then, no matter which one you choose, the game show host asks you to switch. So after you switch, actually you make your choice to get the car become 2/3. Yeah, think about this picture. And we will show you the demonstration on the Jubic notebook. Okay, so that's prepared for the Monty Hole problem. Okay, so the first thing, let's create the goat. We have the first goat and the second goat. So the other goat, we have a function. Since you are the first goat, then the other goat will be the second goat. So that's why here we have a function. So that's according to the beginning choice from the winner. Okay, so then the door we will open is which one. So also we have the other goat. Okay. Yes, of course, depends on. So that's why we run. Yeah, your other goat will be called the function. Okay. Yeah, so that's why here we have 3 choice. Yeah, so that we create the 3 choice behind door on the array. You have 3 choice. So that's we create our Monty Hole games. And then we will run this Monty Hole games 10,000 times. Then you will see, yeah, that will give you the chance. See why you need to switch. So we define the Monty Hole games. Okay, so then you run this game, they will return you 3 data. The first one is your context, the winner original choice. Then what Monty reveal. So then what remaining in the other door. So that's me. If you switch, that's your choice. Okay, so that's why here we give them the choice. You have 3 possible choice. So according to what your original choice, so then we give them the result, right? For example, if they chose to choose the first goat, right, the second goat, that's the Monty will reveal. Then the remaining choice will be car. So that's why they have 3 different results. Right? Okay, so then we run 1 time. Okay, the first thing, let's run the definition. So then we run 1 time. Right? If your first choice if original choice is car, right? They reveal the first goat. Then the result is the second goat. Yeah, you won't believe you need to switch, right? So that's why let's run this game. Okay, for 10,000 times. Then we create the array. Okay, we create the table. So the first thing we create the table, you have guess, reveal, and remaining. Okay, so that's we just run 10,000 times. Okay, you see that's your guess. That's the reveal. That's remaining. Okay, so then we have 10,000 row. So here, because we have 3 different choice, right? So that's why we can group the guess. So after you group the guess, you will according to if your choice, yeah, you see, if your original choice is car, that's how many count. The choice is first goat, how many count. The second goat, how many count. You can see either one, they are almost 1/3. So then we also can group the remaining. Okay, so that's remaining. You can see on the remaining, yeah, actually car become 2/3. Then the rest of that. Okay, so that's why here also we join them as a table. Okay, so that's your item and the original door, then the remaining door. That's me if you switch. So if you see the bar. Okay, so we make that as a bar chart. The blue one, that's me, the original choice. So original choice, right, each door, they are 1/3. But after you switch, right, so actually the yellow one, we don't say you switch, we just say the remaining door. Then remaining door, actually the car become what? Become almost 2/3. Then the rest of that actually become much smaller. So that's what we told you. You always switch. Then you can get your remaining door. You have much higher chance to get the car. Also, that's a chance choice from the blue to the other door. So that's the Monty hole problem.